What if Earth is the dry world? What if Earth is the dry world? What if most truly habitable planets in the galaxy do not look like our continents and clouds blue marble at all, but like frozen white ice balls, hiding global oceans in the dark beneath their crusts? In the hunt for alien life, we usually picture another Earth, blue seas, Greenland, a familiar sky. But while that image feels natural to us, there is a growing suspicion in the data that nature prefers something very different. If water is the key ingredient for life, then planets that are mostly water might be far more common than worlds with thin surface oceans and sprawling continents. This raises a much deeper question. If life prefers oceans, then the real issue is not is there life out there, but how crowded are these alien seas? Are there countless hidden biospheres, sealed under ice shells, quietly thriving in the dark? Or are we one of the rare cases where an ocean world also has air, land, and a transparent atmosphere that lets a star shine directly on the surface? We have built our entire cosmic self-image around that famous photograph of Earth as a blue marble. It feels like the archetypal water planet. After all, more than 70% of our surface is covered by ocean, so it's time to find out the truth. Compared to the rest of the Milky Way, Earth might actually be unusually dry. It should be noted that even in our own solar system, Earth is not the champion of water. Europa, a moon of Jupiter smaller than our moon, may hold twice as much liquid water as all of Earth's oceans combined. Enceladus, a tiny moon of Saturn, sprays plumes of salty water and organic molecules into space. Ganymede, Callisto, Titan, Triton, even distant Pluto and Ceres, all may hide deep global oceans beneath ice. This means that, right here, most potentially habitable environments are not Earth-like planets at all, but buried seas. Now, extend that idea to the entire galaxy. Around other stars, we are finding sub-Neptune and super-Earth planets with low densities and hints of water-rich envelopes. Some may be true ocean worlds, with oceans hundreds or thousands of kilometers deep, capped by high-pressure ice or thick steam atmospheres. Optimistically speaking, there could be more water locked inside these planets than in every ocean of every world in our solar system combined. So, let's begin. In this episode, we will travel from the icy moons of our own system to distant exoplanets that might be almost entirely water. We will try to count every major type of ocean world the galaxy could be hiding, and ask where life would most likely emerge. And as we do, keep one more mystery in mind. New observations from the James Webb Space Telescope are quietly rewriting our estimates of how many ocean worlds exist. The latest numbers are surprising, but we will come back to that. For now, imagine the Milky Way not as a sea of stars, but as a sea of oceans. Why ocean worlds decide the odds of life? If the galaxy is a sea of oceans, which of those oceans can actually host life? In the hunt for alien life, that single question quietly controls almost everything we do. We often hear that follow the water is astronomy's main rule, but why is liquid water so special? It is not magic. It is a solvent that can dissolve a huge range of chemicals, stay liquid across a wide span of temperatures, and carry nutrients and energy around. On Earth, every known cell depends on liquid water. This means, as a working assumption, any truly habitable planet probably needs some kind of ocean, even if it is buried or exotic. So, let's begin with the most familiar category, surface oceans on Earth, like worlds. These are planets where liquid water sits directly under the sky, in contact with an atmosphere and starlight. Earth is the prime example, with continents, a stable climate, and a protective, magnetic field. When we talk about the Goldilocks zone around a star, this is usually what we imagine: a rocky world, moderate temperatures, blue seas, maybe clouds. It should be noted that this picture, while comforting, might be the minority case in the wider universe. The second category is stranger but possibly far more common, subsurface oceans locked beneath ice. Think of Europa and Enceladus orbiting our own star. Both are frozen on the outside, yet the data shows strong evidence for deep global oceans inside. Tidal forces flex these moons, heating their interiors and driving liquid water to slosh above rocky seafloors. Cassini even flew through Enceladus's plumes and found salts, organics, and molecular hydrogen, hinting at hydrothermal vents. No sunlight, no open sky, but all the ingredients for life hidden in the dark. The third category stretches our imagination the most: deep global oceans on water-rich exoplanets. These are super-Earths and sub-Neptunes with so much water that the ocean could be hundreds or thousands of kilometers deep, capped by a dense atmosphere. Some may be hycean worlds with hot steam envelopes and high-pressure ice phases far below. From our telescopes, They often look like featureless dots. We detect their bulk density, their orbit, maybe hints of water vapor, but not the waves themselves. And here is the real difficulty. Oceans are excellent at hiding. A surface ocean can be wrapped in thick clouds. A subsurface ocean can lurk under kilometers of ice. A deep global ocean can sit beneath an opaque atmosphere our instruments cannot yet pierce. So it's time to find out the truth, using indirect clues, tiny dips in starlight, subtle spectral fingerprints, and gravity measurements. Optimistically speaking, if these hidden oceans are common, then the habitable real estate of the galaxy explodes. Instead of a narrow band of Earth twins in perfect orbits, we could be surrounded by countless icy moons, buried seas, and steam-shrouded planets, all quietly testing whether chemistry can become biology. By the end of this video, we will build a mental map of all these ocean worlds, the ones we know, the ones we strongly suspect, and the ones physics almost demands must exist. But first, we need to ask a risky question. What if even our definition of an ocean world is too limited? From TRAPPIST-1 to the ocean galaxy, so, if our definition of an ocean world might be too limited, what actually changed it? In the hunt for alien life, one of the biggest turning points came from systems like TRAPPIST-1. TRAPPIST-1 showed us something radical. A tiny ultra-cool red dwarf, barely larger than Jupiter, can host not one, but 7 rocky, Earth-sized planets. 3 of them sit right around the Goldilocks zone. This means we suddenly had a compact laboratory for habitability, not just a single lucky world. Instead of asking, could this one planet host life? We could compare a whole family, orbit by orbit. But while TRAPPIST-1 is a specific system, its real power is statistical. If one faint red dwarf just 40 light-years away has 7 Earth-sized planets, how many such systems are scattered across the Milky Way? Red dwarfs are the most common type of star in the galaxy. So, let's begin to think in terms of populations. If even a fraction of them look like TRAPPIST-1, we are suddenly dealing with billions of potentially Earth-like planets. Here is where the James Webb Space Telescope quietly shifts the story. Early on, we expected headlines about atmospheres. Does this planet have air, clouds, maybe even biosignatures? Instead, some of the most surprising hints are about composition, the densities, the spectra, the way light filters through those atmospheres, all point towards something deeper, literally deeper. Many of these worlds do not just have a bit of water, they may be dominated by it. Pattern interrupt. What if Earth, the blue planet, is actually water poor? Compared to some exoplanets JWST is probing, Earth's oceans might be a thin film on a mostly rocky surface. Models suggest that a large fraction of planets between Earth and Neptune in size could be water-rich, with global oceans hundreds or even thousands of kilometers deep, capped by high-pressure ice or steam-thick atmospheres. It should be noted that this is not science fiction, it is where the data are quietly pointing. So our question evolves. It is no longer only, is TRAPPIST-1 habitable, or is this one system special? Now we have to ask something far more ambitious. Across the galaxy, what fraction of worlds are ocean worlds in some form? How many have surface seas like Earth, buried oceans like Europa, or entire planets made mostly of water? So it's time to find out the truth. We will follow a familiar arc, start with the big question, then walk through the tools and methods, from icy moons and probes in our own system to dress transit, spectra and mass, radius measurements. Optimistically speaking, that will let us build a framework, and then we will take a systematic tour from nearby ocean candidates to full-on galactic statistics. And along the way, we will confront an unsettling idea. The most common ocean worlds may look nothing like Earth at all, setting us up to flip many of our deepest and most comfortable expectations. How do you even define an ocean world? So if most ocean worlds might look nothing like Earth, what actually counts as an ocean world in the first place? Because if we get this definition wrong, every statistic we build later in the episode will quietly fall apart. In the hunt for alien life, we often picture the classic shot, a blue marble with glittering seas under a friendly star. But while that image is powerful, it is also misleading. When planetary scientists say ocean world, they mean something stricter, and honestly, much stranger. This means a planet or moon with a long-lived, global or near-global layer of liquid water. It does not have to be on the surface. It does not have to look Earth-like at all. So, let's begin with the most familiar class, surface ocean worlds. Earth is the obvious example, with liquid water directly exposed to space, buffered by a breathable atmosphere and warmed by the sun. In principle, a surface ocean world could orbit a red dwarf, sit in a tight Goldilocks zone, and still maintain seas, as long as pressure and temperature allow water to stay liquid. liquid. TRAPPIST-1, for instance, lives in that regime where a surface ocean is at least plausible, depending on the atmosphere we eventually measure. But while surface oceans are intuitive, they might be rare. The second class is probably far more common: subsurface ocean worlds. These are icy moons and dwarf planets where the surface is frozen solid, yet a global ocean hides below. Europa, Enceladus, Ganymede, maybe even Pluto and Ceres all fall into this category. Their trick is pressure and internal heat. A thick ice shell weighs down on the water beneath. Tidal flexing and radioactive decay warm the interior. The surface can be far below freezing, but 100 kilometers down, water flows. It should be noted that this is where phase diagrams quietly rule everything. If we plotted water's state against temperature and pressure, we would see that high pressure can keep it liquid, even when it would normally freeze or boil. Under a massive ice lid, or under a thick atmosphere, water can occupy exotic regimes, liquid layers, high-pressure ices, even supercritical fluids that are neither classic liquid nor gas. That brings us to the third class: water-rich exoplanets with deep, high-pressure oceans and steam envelopes. Many sub-Neptune worlds seem too low density to be rock alone. JOIS data suggests some of them could be wrapped in thick atmospheres overlying oceans thousands of kilometers deep, with the bottom crushed into high-pressure ice. Inside this group sits a particularly intriguing idea: hycean planets. These are worlds with global oceans and hydrogenic atmospheres, warm enough at the top for liquid water, but supported by a deep envelope more like a mini Neptune. Optimistically speaking, their large sizes and puffy atmospheres make them ideal targets for dress transmission spectra and potential hunting grounds for biosignatures. So it's time to find out the truth. If we count surface oceans, buried oceans, and deep hycean seas, is Earth really the template for ocean worlds, or is it the odd one out? In the next section, we will start putting actual names and numbers to these categories, from our own solar system to the exoplanet census, the solar system's secret ocean inventory. So if Earth might be the odd one out, what does our own backyard really look like when we start counting oceans instead of continents? In the hunt for alien life, this is where the story quietly becomes much stranger than most of us were taught in school. When we picture an ocean world, we instinctively imagine a blue marble like Earth. But while Earth advertises its water from space, most of the ocean worlds in our solar system are masters of disguise. Their seas are buried under ice, wrapped in haze, or locked deep inside frozen dwarf planets. This means that for decades, we simply did not realize how water-rich our local system actually is. So, let's begin with the headline act: Europa. This small moon of Jupiter is only slightly smaller than our own moon, yet under its cracked, bright ice shell, the data point to a global ocean, not a few scattered lakes, but a continuous, planet-wide sea. It should be noted that estimates suggest Europa may hold about twice as much water as all of Earth's oceans combined. A tiny world with a truly enormous ocean. If that does not reframe what an ocean planet can be, what will? Europa is not alone. Enceladus, a moon of Saturn, blasts plumes of salty water and organic molecules into space, direct evidence of a liquid ocean and hydrothermal activity at its seafloor. Ganymede and Callisto, also around Jupiter, almost certainly hide deep internal oceans beneath thick ice layers. Titan, with its dense atmosphere and surface lakes of liquid hydrocarbons, likely also hosts a vast subsurface water ocean below the crust. Even Triton around Neptune, Pluto far beyond, and the dwarf planet Ceres in the asteroid belt show signs that they either hosted or still host internal oceans. So on a simple count, we have at least 9 suspected or confirmed ocean worlds in one planetary system: Europa, Enceladus, Ganymede, Callisto, Titan, Triton, Pluto, Ceres, plus Earth itself, and we are still debating others. Optimistically speaking, the more we look, the more oceans we seem to find. But the real twist is deeper. Uranus and Neptune, the ice giants, are thought to contain enormous internal layers of water mixed with other volatiles, forming superheated, high-pressure oceans that never see starlight. If 2 of the major planets in our system are essentially water-rich giants, this means that water is not an exotic ingredient at all. It is a standard outcome of planet formation beyond the snow line. So it's time to find out the truth. If one ordinary star system can hide this many oceans, what happens when we scale that up to the hundreds of billions of stars in our galaxy, and then to the entire universe? Earth, the oddball shallow ocean world. We like to think of Earth as the ultimate water planet, but what if our blue marble is actually one of the shallowest ocean worlds in the galaxy? So, let's begin with a slightly uncomfortable number. If we could magically scrape up every drop of liquid in Earth's oceans, ice caps, lakes, and rivers, and spread it out evenly over the surface, the result would be a global ocean only about 3 kilometers deep on average. 3 kilometers sounds impressive, until we remember that suspected oceans inside moons like Europa may be tens or even over 100 kilometers deep, and hycean exoplanets could have water layers that go down for thousands of kilometers. This means that, by cosmic standards, Earth is surprisingly dry. Our oceans cling to a thin crust above a huge rocky mantle, instead of dominating the whole planet, and they are exposed. Earth's seas sit directly under an atmosphere, in contact with space, climate cycles, and every solar tantrum our star throws at us. It should be noted that this makes them fragile. Change the greenhouse gases slightly, dim the sun a bit, or shift the continents, and large parts of the ocean can freeze or evaporate. Now, compare that to the buried oceans of Europa, or Enceladus. Their water is locked under tens of kilometers of ice, shielded from radiation, flares, and vacuum. No storms, no direct loss to space. As long as tidal heating from their orbit and radioactive elements in their cores keep supplying energy, those oceans can stay liquid for billions of years, even far beyond the classical Goldilocks zone. Here is the twist. We usually define a habitable planet as something Earth-like, with surface oceans under a friendly sky. But while we rely on a narrow orbit, a stable atmosphere, and just the right distance from the sun, subsurface ocean worlds play by different rules. In the hunt for alien life, that might be a huge advantage. They do not care if their star is bright, dim, or even if they drift through the universe with no star at all, as long as internal heating continues. Pattern interrupt. Imagine zooming out from the famous image of Earth, that glowing blue disk. Now, overlaid next to it, a cutaway of Europa, a small icy moon with perhaps twice Earth's water. Next to that, a hycean planet, most of its volume a crushing global ocean. Suddenly, our proud blue marble looks like a thin, wet film. Optimistically speaking, Earth-like surface oceans may not be the default solution for liquid water. They might be the minority. So it's time to find out the truth. If deep, hidden oceans are easier to make and easier to keep stable, where should we really be looking next? Europa, the prototype hidden ocean world. If most of the galaxy's oceans are hidden under ice, how do we study seas we can't even see? In the hunt for alien life, we need a prototype. A place where we can test every trick we have for detecting a buried ocean from orbit alone. So, let's begin with Europa. Europa is smaller than our moon, but when we first look at it, it almost feels like we are staring at an eyeball of the outer solar system. The surface is bright, nearly pure water ice, crisscrossed by long, rust-colored fractures that wrap around the entire planet. There are very few impact craters. That is important, because it means the surface is young and constantly being resurfaced. Something underneath is flexing, cracking, and healing this frozen shell. But while the surface looks frozen solid, the patterns of those cracks tell us the ice behaves almost like a floating plate. Tidal forces from Jupiter pull and squeeze Europa as it orbits, and the ice responds more like a thin crust over a liquid layer than like a rigid frozen block. This is our first hint that there is something mobile, and very likely global, below. The decisive evidence, however, came from a magnetic whisper. The Galileo spacecraft measured how Jupiter's powerful magnetic field swept through the Europa system. The field kept changing in a way that did not match a simple solid world. Instead, the data showed signs of an induced magnetic field, created when a conductive layer inside Europa had electric currents driven through it. This means there is a salty, electrically conductive ocean beneath the ice, responding like a planetary-scale dynamo. It should be noted that this is not a small underground lake. Models suggest Europa's global ocean may hold about twice as much water as all of Earth's oceans combined, wrapped around a rocky interior. For a world smaller than our moon to outwater the water planet is a profound reminder that surface appearance can be deeply misleading. So what about habitability? At the bottom of that ocean, where liquid water meets a rocky seafloor, tidal flexing could drive hydrothermal vents, just as on Earth's mid-ocean ridges. There, chemical gradients between hot, mineral-rich fluids and colder surrounding water could power metabolism, even in total darkness. Optimistically speaking, if life can arise wherever there is water, energy, and chemistry, Europa becomes one of the most promising habitable environments in the entire solar system. This is why NASA's Europa Clipper mission is being built as a dedicated ocean detective. It will map the ice shell, taste the thin atmosphere, and search for plumes that might briefly connect the hidden sea to space. If we can read Europa's interior from orbit, we can apply the same logic to distant exoplanets. But Europa may not be the easiest place to sample an alien ocean directly. For that, we might need a world that is not just leaking hints of its sea, but actively spraying it into space. Enceladus, the moon that sprays its ocean into space. So if Europa only leaks hints of its ocean, what happens when a world simply sprays its ocean straight into space? In the hunt for alien life, that is almost the perfect shortcut. No drilling, no melting, just flying through the mist of an alien sea. So, let's begin with one of the most unlikely places in the Saturn system. Enceladus is tiny, barely 500 kilometers across, an ice-covered moon that should have been geologically dead for billions of years. Yet when the Cassini spacecraft arrived, it found something no one expected. From the South Pole, enormous plumes were erupting, jets of vapor and ice crystals shooting hundreds of kilometers above the surface like frozen geysers. How can such a small, cold moon power that kind of activity? Cassini did not just watch from a distance, it dove straight through those plumes, using its instruments as a kind of cosmic chemistry lab. The data revealed salty water, the same kind of salts we find in Earth's oceans. It detected complex organic molecules, the carbon-based building blocks of life, and crucially, it found molecular hydrogen, H, streaming out of the interior. This means Enceladus is not just a ball of ice with a quiet ocean. Molecular hydrogen is a telltale sign of water reacting with hot rock on the seafloor, a process called hydrothermal activity. On Earth, at deep-sea vents, the same kind of chemistry feeds entire ecosystems of microbes, which in turn support larger organisms. But while our planet needs sunlight at the surface, these vent communities live entirely off chemical energy. It should be noted that molecular hydrogen is especially important because it is an energy source that simple microbes can use directly. If you were designing a habitable environment hidden beneath ice, you would ask for liquid water, organics, and a steady supply of chemical fuel. Enceladus appears to check every box inside a moon the size of a major Earth city. And here's the astonishing part. Unlike Europa, which keeps its ocean sealed, Enceladus is effectively venting its ocean into space. Every plume particle is a tiny sample of the global sea. For a spacecraft, this is a dream scenario. You do not have to land, or drill, or survive crushing pressure. You simply orbit through the plume, collect the frozen spray, and taste an alien ocean directly. Optimistically speaking, if there are microbes in that water, fragments of their chemistry might already be drifting into space above the South Pole, waiting to be caught. So it's time to find out the truth. If a small, fragile moon around Saturn can host a warm, chemically active ocean, how many similar worlds are quietly orbiting other stars, venting their seas into space where we will never send a probe, but might still read their signatures from light years away? The giant ocean moons, Ganymede, Callisto, Titan, Triton. If Enceladus and Europa are just the opening act, what happens when we look at the true giants of the outer solar system? Because around Jupiter and Saturn, entire miniature planetary systems are hiding worlds that are even stranger. So, let's begin with Ganymede and Callisto, the heavyweight moons of Jupiter. At first glance, they look like dead, frozen craterscapes, but while their surfaces seem quiet, the data tell a different story. Ganymede, the largest moon in the solar system, has its own magnetic field. When Jupiter's charged particles sweep past, they induce a secondary signal deep inside, best explained by a global salty ocean wrapped in ice. Callisto, farther out and less disturbed by Jupiter's gravity, shows a similar magnetic response and fits models that place a buried ocean hundreds of kilometers down. This means even the old cold outer moons can hide entire seas. No sunlight, no blue waves, yet still potentially habitable environments. Warmed from within by the slow decay of radioactive elements and, in Ganymede's case, gentle tidal flexing. Titan, around Saturn, takes the idea of an ocean world and turns it into a layered puzzle. On the surface, rivers, lakes, and even seas of liquid methane and ethane fill its polar regions under a thick orange atmosphere, richer in organics than anywhere else we know. It should be noted that this is not water. At Titan's frigid temperatures, methane plays the role that water plays on Earth, but radar and gravity data from the Cassini mission suggests that beneath its ice shell lies yet another ocean, this time made of liquid water mixed with ammonia. So, Titan may host two stacked oceans of completely different chemistry, one of hydrocarbons, one of water. Farther out, Neptune's moon Triton and even the dwarf planet Pluto push this idea to the edge of the solar system. Triton likely began life as a captured Kuiper belt object, then was kneaded by intense tides when it settled into its odd retrograde orbit. That early heating, plus ongoing radiogenic warmth, may have left a residual subsurface ocean under its thin nitrogen frost. Pluto, once thought utterly frozen, now fits models where a buried ocean survives, insulated by exotic ices. In the hunt for alien life, that diversity matters. Some of these oceans are probably laced with salts or ammonia, lowering their freezing points and reshaping their chemistry. Optimistically speaking, that could expand the range of habitable conditions far beyond Earth like seas. So it's time to find out the truth. If a single gas giant system can host multiple ocean moons, what happens in exoplanet systems packed with super-Earths and mini-Neptunes, where entire planets might be mostly water? Ceres, Pluto, and the marginal seas of the deep freeze. So if giant planets can host entire families of ocean moons, what about the tiny worlds we usually ignore? Could something as small as an asteroid-sized dwarf planet really hide an ocean, or even a ghost of one, under its skin? To answer that, we have to visit Ceres, the largest object in the asteroid belt. At first glance, Ceres looks like a dull, dark rock, but while it orbits quietly between Mars and Jupiter, the data from NASA's Dawn mission showed something far stranger. Gravity measurements hinted that Ceres is not uniform inside. Some regions are less dense, some more, suggesting layers. Combined with bright salt deposits on the surface, this means Ceres once had, and may still have, salty liquid brines moving underground. It should be noted that those bright spots in Ocator Crater are not just cosmetic. They are evaporated minerals left behind when water-rich fluids rose up from below and froze or boiled away into space. That is classic ocean world behavior, just on a smaller scale. In the hunt for alien life, a dwarf planet quietly circulating in our own solar system suddenly starts to look less like debris and more like a very compact laboratory. Now we head to the edge of the Sun system, to a world we once called a planet, then downgraded, and then rediscovered as something even more exotic. Pluto. When New Horizons flew past in 2015, we expected an ancient, frozen crater ball. Instead, we saw smooth, young plains, towering water ice mountains, and hints of cryovolcanoes that may have erupted slushy mixtures of ice and liquid. That surface is far too active for a solid, frozen block. So, what keeps Pluto moving inside? Models suggest a deep internal ocean, insulated by thick layers of nitrogen and methane ices that act like a thermal blanket. Radioactive elements in Pluto's rocky core slowly release heat, just enough to keep a buried ocean from freezing solid, even billions of years after formation. Optimistically speaking, that makes Pluto less a frozen relic and more a slow, cold engine, quietly running in the dark. Here's the bigger surprise. Many icy bodies may pass through an ocean phase early in their history. Short-lived heat from radioactive decay, impacts, and tidal flexing can melt internal ice for tens or hundreds of millions of years. Then the heat fades, the ocean freezes, and from the outside, the world looks dead. But for that brief window, it held a global sea. So it's time to find out the truth. Are oceans really rare, central features like Earth's, or are they just one more temporary layer that small worlds cycle through? If even dwarf planets and large asteroids can host brains, then hidden seas might be the rule, not the exception. Pattern interrupt. Pull back from Pluto. Imagine the Kuiper Belt as a vast, dim ring of ice and rock surrounding the Sun, filled with countless Plutos, mini-Plutos, and Ceres-like bodies. How many of those silent, frozen objects once held dark oceans or still hide them now, completely unseen? This means that when we look outward to exoplanet systems, we should not only be searching for big blue Earth-like planets, we should be asking a deeper question. How many small, cold, easily overlooked worlds are quietly hiding water, and how could we ever detect their oceans from light years away? From backyard census to galactic ocean math. So, if our own backyard might be packed with hidden oceans, what does that actually mean for the rest of the galaxy? Because before we scale up, we should be very clear about what we have already found at home. In the hunt for alien life, we usually start with Earth's surface oceans as our mental template. But when we take a census of the solar system, Earth is just one entry on a surprisingly long list. Europa alone may hold twice as much water as all of Earth's oceans. Enceladus is spraying salty plumes from a global sea. Ganymede and Callisto probably hide deep layers of liquid. Titan and Triton almost certainly do as well. It should be noted that this list does not stop with the big moons. Pluto and maybe even Ceres show signs of past or present internal oceans. That means we are looking at least half a dozen strong ocean world candidates, and several more that are plausible, all in one fairly ordinary planetary system, not a special one near the center of the galaxy, just a random star in a spiral arm. So, let's begin the extrapolation. If a single, average-looking star with 8 major planets, some dwarf planets, and a cloud of small icy bodies already hosts many oceans, how unusual can that be? Statistically speaking, if you draw one marble from a bag and it is striped, you start to suspect a lot of striped marbles inside. Our striped marble is the solar system. But why are there so many icy, water-rich objects in the first place? The answer begins with a simple, powerful idea in planet formation, the ice line. This is the distance from a young star where water vapor in the protoplanetary disk freezes into solid ice grains. Inside that line, water stays as gas. Beyond it, it locks onto dust. This means that just past the ice line, there is suddenly much more solid material available. Planetesimals grow faster, and they naturally incorporate huge amounts of frozen water. Over time, these bodies can become moons, dwarf planets, or full-sized planets that either stay beyond the ice line or migrate inward, carrying their water with them. So here is the key scaling question. If almost every young star has a disk with an ice line, and our galaxy holds hundreds of billions of stars, how many ocean worlds might be out there? Tens of billions? Hundreds of billions? Could water-covered or water-filled planets actually outnumber dry, rocky ones like Mars? Optimistically speaking, the answer might be yes, but so it's time to find out the truth using more than back-of-the-envelope guesses. Our exoplanet surveys, and now detailed spectra from the James Webb Space Telescope, are finally giving us hard data on water-rich planets. The twist is that the first confirmed ocean worlds out there do not look like Earth at all. Meet the exoplanet ocean candidates, sub-Neptunes and hyceans. So, if the first ocean worlds out there do not look like Earth, what do they look like? In the hunt for alien life, this is where things become strange very quickly. When astronomers started finding exoplanets in large numbers, something immediately stood out. Most of the planets we detected were not Earth-sized rocks or giant Jupiters. Instead, there was a huge population in between, worlds 2 to 4 times Earth's radius, with a few to 10 times Earth's mass. We call them super-Earths and sub-Neptunes, and it should be noted that nothing like them exists in our own solar system. This means our local backyard is a poor guide. Around other stars, these intermediate planets seem to dominate. Many orbit closer to their star than Mercury does to the Sun, completing a full orbit in just a few days. But while their orbits are tight, their internal structures may be very different. Are they mini-Neptunes wrapped in thick gas, or are some of them essentially giant water worlds? Planet formation models and density measurements are starting to give us an answer. If you compare a planet's mass and radius, you can estimate how much of it must be rock, gas, or water. For a surprisingly large fraction of sub-Neptunes, the numbers only make sense if a lot of their bulk is water or other volatiles. Some studies suggest that perhaps 30% or more of these planets could be water-rich, with global oceans tens to hundreds of kilometers deep, capped by high-pressure ice far below the surface. So, let's begin to narrow this down even further. A particularly exciting subset are the so-called hycean planets. Picture a world a few times larger than Earth, wrapped in a hydrogen-rich atmosphere, with a vast, continuous ocean underneath. The deep interior might be an exotic mix of high-pressure ice and rock, but at the interface between the atmosphere and the upper ocean, conditions could be temperate, with liquid water and energy from the star. In other words, there might be a broad, habitable layer floating on top of a truly alien sea. Hycean planets matter because they are, quite simply, easier to study. Their large size gives them more area to block starlight during a transit. Their puffier atmospheres imprint deeper spectral fingerprints when the planet crosses in front of its star. For telescopes like JWST, that is a dream scenario. Instead of struggling to tease out a whisper-thin Earth-like atmosphere, we can read the signatures of molecules in hycean atmospheres with far greater confidence. Optimistically speaking, that makes them prime targets. If biosignature gases build up in those hydrogen envelopes, we might detect them decades before we can do the same for a true Earth twin in a classic Goldilocks zone. So it's time to find out the truth. Could the first clearly habitable or even inhabited planet we confirm be a hycean world and not an Earth clone at all? And if so, what would alien life look like in an ocean thousands of kilometers deep? Droost. The ocean detector in deep space, if alien life is swimming in those abyssal hycean seas, how could we possibly know from tens or hundreds of light years away? In the hunt for alien life, we do not get close-up photographs first. We get spectra, thin, spiky rainbows of light. This is where the James Webb Space Telescope becomes our ocean detector in deep space. Webb was built for the infrared, the wavelengths where cool planets, water vapor, and complex molecules quietly glow. Its mirror is huge, 6.5 meters across, gathering faint photons that older telescopes would simply lose to the darkness. And crucially, it can watch as a planet slips in front of its star and take what is called a transmission spectrum. What does that mean in practice? As the planet transits, a tiny fraction of starlight filters through its atmosphere. Different gases absorb different colors of infrared light, carving out a barcode in the spectrum. By measuring that barcode, we can infer whether the atmosphere is rich in hydrogen, loaded with water vapor, or cloaked in high clouds. We never see the ocean directly, but we can read its fingerprints in the air above. This means that if a planet has a deep global ocean feeding water vapor into a relatively clear atmosphere, we might see strong broad water features. If instead it is a steam world, with temperatures so high that the ocean is more like a pressure cooker, we might see an even thicker, more extended water-rich envelope. And if the world is smothered in hazes or clouds, those features can flatten out, hinting at hidden layers we cannot quite reach. Early JS results are already teasing us. Several sub-Neptunes, planets between Earth and Neptune in size, show spectra that are consistent with water-rich or steam-dominated atmospheres. Some appear to have hydrogen blankets laced with water, others look almost completely muted, as if high-altitude clouds are blocking our view. It should be noted that interpretations are still debated, with different teams arguing over how much water, how many clouds, and what this implies for any underlying ocean. But while Webb is powerful, it is not all-seeing. JWST cannot easily peer through extremely thick clouds or hazes, and it cannot yet map coastlines or distinguish every possible ocean configuration. A shallow ocean under a dense atmosphere can look surprisingly similar to a deep ocean under a thinner one. What it can do is rule out some scenarios and favor others. No hydrogen envelope here, no dry rocky surface there, perhaps a water-rich mantle instead of a barren desert. Optimistically speaking, we are already moving from is there an atmosphere to what kind of ocean world might this be, and one planet has become the poster child for this new era. K2-18b and a handful of similar sub-Neptunes may be worlds where JWST is seeing the breadth of possible alien oceans, so it's time to find out the truth. What exactly has Webb seen in the skies of K2-18b? And could those signals really point to a living ocean beneath? Case study, K2-18b and the hycean debate. K2-18b is the perfect stress test for our ideas about ocean worlds. Is it a mini Neptune wrapped in gas, or a true water world with alien seas hiding under clouds? In the hunt for alien life, that difference matters enormously. This planet orbits a cool red dwarf about 124 light-years away, sitting right in its star's Goldilocks zone. It's roughly 2.6 times Earth's radius and about 8.6 times Earth's mass, so it is not an Earth-like rocky world. Instead, it falls into the mysterious sub-Neptune category, the most common type of planet we know of in the galaxy, but one we do not actually have in our own solar system. That alone makes it both exciting and frustrating. So, let's begin with what we have actually seen. Hubble first hinted that K2-18b has a hydrogen-rich atmosphere with traces of water vapor. Then JWST stepped in with far sharper vision. Its infrared spectra again showed water features and a puffy, low-density atmosphere that, at first glance, looked consistent with some hycean models. Worlds with deep global oceans under thick hydrogen blankets, potentially still habitable despite high pressures. But while the headlines rushed ahead, the science is much more cautious. One early analysis claimed tentative signs of dimethyl sulfide, or DMs, a gas on Earth that is strongly linked to marine life. That sounded explosive. A possible biosignature on an ocean world? This means instant news coverage. Yet when other teams reanalyzed the same data with different assumptions, the DM signal largely vanished into the noise. Pattern interrupt. Imagine trying to hear a whisper in a stadium while 1,000 people shuffle their feet. That is what we are doing with these spectra. It should be noted that JWST is operating at the very edge of what is currently possible. Tiny wiggles in the spectrum can be created by the instrument, by the star, by the planet's clouds, or by how we process the data. Optimistically speaking, DMs is an interesting hint. Realistically, it is not evidence for life yet, and may simply be an artifact or a misinterpretation of overlapping features like methane and carbon dioxide. So what is K2-18b actually like? Modelers can fit the data with a range of structures. One option is a mini Neptune, a deep hydrogen, helium envelope with water compressed into a supercritical layer at immense pressures, far from anything we would call a surface ocean. Another option is a more modest ocean world, a water-rich interior, a global sea under high clouds, and a thinner hydrogen atmosphere that JWST can probe. Both scenarios, and many in between, are still allowed. That is the real lesson here. We are learning to read the atmospheres of distant planets for the first time, but our vision is still blurry. Definitive proof of an actual ocean on K2-18b is out of reach for now, so it's time to find out the truth on a larger scale. If individual worlds are this uncertain, what can we really say about how common ocean planets are across the galaxy? galaxy. How planet formation favors water-rich worlds. If our measurements of individual planets are so uncertain, maybe we should flip the question. Instead of asking whether a specific world has an ocean, we should ask, does the way planets form naturally favor oceans in the first place? So, let's begin with the birthplaces of planets. Protoplanetary disks. These are vast, rotating pancakes of gas and dust around a young star. Close to the star, temperatures soar. Only metals and rock can survive there, so this inner zone tends to build dry, rocky planets. But move outward, and you reach a critical boundary called the ice line. Beyond this distance, water and other volatiles actually freeze onto dust grains, turning them into icy pebbles. Farther still, in the outer disk, almost every grain is coated in ice. This means that, from the start, most of the solid material in a planetary system is not rock. It is ice-rich, and that has huge consequences, because once those icy pebbles start clumping together into kilometer-sized planetesimals, they become the building blocks of future planets. The question is, do they stay out there, or do they move? Planet formation models tell us they move. A lot. Interactions with the gas in the disk can cause entire planets to migrate inward, and smaller icy bodies can be scattered throughout the system. Icy planetesimals that formed beyond the ice line can spiral inward and smash into young rocky worlds. Each impact is a delivery of water and volatiles. Over millions of years, this process can transform a dry embryo into a water-rich super-Earth, or even a sub-Neptune, with a deep global ocean wrapped in a thick atmosphere. It should be noted that when astronomers run simulations of this process, something striking keeps appearing. They do not just get one Earth-like planet with a thin veneer of oceans. They often produce many planets with enormous water fractions, 10%, 20%, sometimes more of the planet's mass in water and ices. By comparison, Earth's oceans are a rounding error, only a tiny fraction of a percent of our planet's mass. In the hunt for alien life, that difference matters. If ice is abundant beyond the ice line, and migration is common across the galaxy, then ocean worlds are not rare accidents. They are the statistical default. We should expect countless planets with global oceans hundreds of kilometers deep, high-pressure ice mantles, and dense, steam-rich atmospheres, orbiting not just sun-like stars, but also red dwarfs in their own compressed Goldilocks zones. Optimistically speaking, that sounds like a universe overflowing with potential habitats. But it also raises an uncomfortable possibility. Maybe Earth, with its modest seas and exposed continents, is the strange one. Maybe our planet's finely balanced water budget required just the right amount of delivery and just the right amount of loss. So what does that mean for which ocean worlds are actually habitable? Surface oceans versus buried seas, which are rarer? So, if Earth might be the oddball, we have to ask a very uncomfortable question. Which kind of ocean is actually rare in the universe? Because not all oceans are created equal. Surface oceans like ours are divas. They need almost everything to go right at once. The planet has to sit in the Goldilocks zone of its star, close enough to keep water from freezing solid, but not so close that it boils away. It also needs a stable climate, a protective atmosphere to hold in heat without going full Venus, and, crucially, only a relatively thin layer of water. Too little, and you get a dry world. Too much, and you drown the continents. This means an Earth-like surface ocean is balanced on a knife edge between iceball and steam bath. Change the orbit slightly, brighten the star a little, strip away the atmosphere with flares from a red dwarf, and that calm blue surface disappears. In the hunt for alien life, we love these familiar seas, but statistically, this level of fine-tuning may be extremely hard to achieve, and even harder to maintain for billions of years. Subsurface oceans play by a different rulebook. They do not care much about the Goldilocks zone. All they really need is internal heating and enough insulating ice on top to trap it. Radioactive elements in the interior, leftover heat from formation, or tidal flexing from a giant planet can keep water liquid under an icy shell, even far from the sun. It should be noted that Europa, Enceladus, Ganymede, Callisto, Titan, Triton, and probably Pluto and Ceres all seem to hide global or regional buried seas. So while Earth has one surface ocean, our solar system may have at least half a dozen subsurface ones. Extrapolate that to the galaxy, and suddenly, frozen-looking worlds become prime real estate. Optimistically speaking, the average habitable ocean might be locked away in darkness, under tens of kilometers of ice. Then, there are deep exo-oceans on water-rich planets, the true heavyweights. These worlds may hold oceans hundreds or thousands of kilometers deep, wrapped around a rocky core, but capped on the bottom by exotic high-pressure ice phases that form when water is squeezed hard enough. That icy layer can act as a barrier, limiting direct contact between liquid water and rock. and potentially starving any ocean life of the minerals and energy that seafloor chemistry provides on Earth. So, let's begin to be brutally honest with our statistics. Formation models, plus JBUS data hinting that many sub-Neptunes and super-Earths are water-rich, suggests that buried in deep oceans could outnumber exposed surface oceans by a large factor, perhaps by tens or even hundreds to one. So it's time to find out the truth. If most oceans are hidden under ice or crushed beneath high pressure, what does that really mean for life's chances and for our ability to spot living seas from light years away? Can life thrive in dark, high-pressure oceans? So if most oceans are hidden, the obvious question is this: can life really thrive in endless darkness, under pressures that would crush a submarine? In the hunt for alien life, deep sunless water used to feel like a deal-breaker, but our own planet quietly proves that it is not. Far below Earth's surface oceans, where sunlight never reaches and the water is near freezing, we find hydrothermal vents splitting the seafloor. Around them, entire ecosystems bloom, powered not by light, but by chemistry. Giant tube worms, clams, shrimp, and dense bacterial mats all tap into chemical energy released as hot, mineral-rich water jets out of the crust. This means that even on Earth, the rules for a habitable ocean are already broader than a simple need for starlight. So, let's begin with the key idea. Life does not care whether energy starts as sunlight, as long as that energy can be captured in molecules. At Earth's vents, microbes use hydrogen sulfide, methane, and hydrogen to drive chemosynthesis, building organic matter in total darkness. It should be noted that these communities can be surprisingly rich, rivaling coral reefs in local biomass, all sustained by rock-water reactions rather than the sun. Now imagine Europa or Enceladus. Both orbit within the gravity fields of giant planets that constantly flex their interiors. That tidal heating, combined with the decay of radioactive elements in their rocky cores, keeps water liquid and drives hydrothermal activity at the seafloor. Cassini has already seen molecular hydrogen in Enceladus's plumes, a direct hint of water-rock interactions that could feed chemosynthetic microbes. Optimistically speaking, the same physics should operate on countless icy moons and water-rich exoplanets orbiting distant stars. But while the energy is there, these deep oceans face serious challenges. Pressure climbs to hundreds or thousands of atmospheres, changing how water behaves and how chemistry runs. On very deep exo-oceans, high-pressure ice layers may form between the liquid and the rocky core, sealing the water away from fresh minerals. With little contact between rock and ocean, nutrient cycling could stall, leaving only thin, energy-poor habitats. So it's time to find out the truth about what this would feel like up close. Forget the galaxy for a moment. Picture a single alien vent chimney rising from a black seabed on a planet orbiting a faint red dwarf. Superheated water roars out, rich in hydrogen and exotic metals. Around it, translucent worms pulse with slow, deliberate movements, while mats of dark microbes coat the rock like velvet. No sky. No day or night, just chemistry, pressure, and time. In a place like this, photosynthesis might never evolve, or remain confined to a thin, unreachable surface. Yet chemosynthesis could still sustain vast microbial biospheres, spread through cracks and vents, almost invisible to our telescopes. From light years away, such a world might look dead, its atmosphere quiet, its spectrum plain. The life would be there, but hidden, forcing us to rethink what a truly habitable ocean world looks like. And if most living seas are like that, then our next challenge is clear: how do we detect what we cannot see in planets whose oceans never meet the sky? Biosignatures above an invisible ocean. So, if the ocean never touches the sky, what exactly are we supposed to look for? In the hunt for alien life, that question pushes us straight into the world of biosignatures. When astronomers say biosignature here, we are really talking about clues, not proof. These are things like strange mixtures of gases in a planet's atmosphere, chemical imbalances that should not persist without something constantly renewing them, or even large-scale surface patterns that are hard to explain without biology. Oxygen next to methane, for example, is a classic red flag. Left alone, those two destroy each other. If they both keep showing up, something is feeding them. On water-rich exoplanets and hycean worlds, that is exactly the kind of imbalance G West is trying to catch. These planets might have deep global oceans under thick, steamy atmospheres, or even hydrogen-rich envelopes that trap heat and keep the surface liquid far outside the traditional Goldilocks zone. So, let's begin with what light can tell us. As a planet passes in front of its star, starlight filters through the atmosphere. Molecules like water vapor, carbon dioxide, methane, oxygen, and maybe even more exotic gases leave a fingerprint in the spectrum. This means we can, in principle, measure not just what what is there, but how much, and whether that mix looks like simple chemistry or something more restless. It should be noted that this is already hard for a single Earth-like world. Now stretch that challenge to a mini Neptune, with clouds, hazes, and maybe storms that blur everything together. Dwest can search for broad hints, methane with carbon dioxide but not much carbon monoxide, or unusual nitrogen compounds could all point to active chemistry. Optimistically speaking, a hycean planet with a relatively clear atmosphere might shout its disequilibrium at us across light years, but subsurface ocean worlds raise the stakes. If Europa, Enceladus, or Titan were exoplanets, their oceans would be completely sealed under ice, with almost no direct gas exchange with the sky. Life could thrive around hydrothermal vents, rich in energy and chemistry, yet the atmosphere above might look plain, dominated by simple molecules that tell us almost nothing. From another star system, such a world would appear quiet, maybe even dead. So how do we get around that? One speculative idea is plume activity, like we see on Enceladus, where jets of salty water and organic molecules escape through cracks in the ice. If an exomoon around a distant giant planet had similar plumes, they might briefly thicken its atmosphere or leave faint spectral traces during transit. Another possibility is tectonic resurfacing. If internal oceans lubricate an ice shell, they might drive slow, global ice plate tectonics, constantly renewing the surface with fresh, bright ice or strange chemistry we do not expect. So it's time to find out the truth. Even if most alien oceans are invisible, can we at least count how many there are, map where they orbit their stars, and see which ones might be close enough for us to reach, or even one day explore directly? How many ocean worlds are in the Milky Way? So if most alien oceans are invisible, how many of them are actually out there with us in the Milky Way? Are we talking about a handful of rare jewels, or an entire galaxy where oceans are the rule rather than the exception? To answer that, we have to zoom out. Over the last decade, exoplanet data from missions like Kepler and TESS has made one thing very clear: most stars have planets. Not just one lonely world, but full planetary systems, with multiple planets packed into orbits far tighter than our own solar system. And a huge fraction of these fall between Earth and Neptune in size, right in the regime where water and thick atmospheres can dominate. This is where formation models come in. When planets form beyond the ice line of a star, they build up enormous amounts of frozen water and other ices. If they later migrate inward, that ice can melt into global oceans or become high-pressure water layers thousands of kilometers deep. It should be noted that several independent models now suggest that perhaps 30% or more of Earth to Neptune-sized planets could be water-rich, not dry rocky worlds like Mercury. In the hunt for alien life, that single percentage is astonishing, because we are not counting a few dozen planets. We are dealing with hundreds of billions of planets across the galaxy. This means that even a conservative water-rich fraction translates into tens of billions of potential ocean worlds, some with surface seas, others with buried high-pressure oceans hidden beneath ice. But while we often focus on planets, our own solar system reminds us that moons matter just as much. Around two gas giants, Jupiter and Saturn, we already have Europa, Ganymede, Callisto, Enceladus, and Titan as strong ocean world candidates, with more suspects like Triton and even Pluto farther out. One planetary system, one star, and yet at least half a dozen possible oceans beyond Earth. Optimistically speaking, that is our local control sample. So, let's begin a rough count. The Milky Way contains perhaps 100 to 400 billion stars. Many are red dwarfs, smaller and cooler than the Sun, but excellent at holding onto compact systems of Earth-sized and super-Earth planets in tight orbits, sometimes in a permanent Goldilocks zone. Suppose only half of all stars host planets, and each such system averages just 2 worlds in the Earth to Neptune range. That already gives on the order of 100 to 400 billion of these planets. Now apply that modest 30% water-rich estimate. Suddenly, we are looking at tens to over 100 billion planetary ocean worlds before we even add icy moons. If even a fraction of giant planets host moon systems like Jupiter's or Saturn's, the number of subsurface oceans could easily multiply again. So it's time to find out the truth. Are these back-of-the-envelope numbers right? And how will telescopes like JEST and the next generation actually confirm which of these distant worlds are truly wet and which are dry imposters? Red dwarfs, flares, and the fate of their oceans. If most of those oceans are real, then we have to ask a deeper question. Where in the galaxy are they actually hiding? In the hunt for alien life, that question leads us straight to the most overlooked stars of all. Red dwarfs, or M-dwarfs, are the quiet background chorus of the Milky Way. They are small, cool, and incredibly common. It should be noted that roughly 3 out of every 4 stars in our cosmic neighborhood are red dwarfs. Proxima Centauri is one, TRAPPIST-1 is another. This means that if ocean worlds form easily, a huge fraction of them should end up packed around these tiny, long-lived stars. But while our sun hosts a spread-out family of planets, red dwarfs often gather their worlds into compact systems. Many of them show chains of Earth-sized and sub-Neptune planets, all crammed closer to the star than Mercury is to the sun. Their Goldilocks zone is tucked in tight, so a habitable orbit might take only a few days. At first glance, that sounds perfect. Lots of small, potentially Earth-like planets, all easy to detect. So, what is the catch? The problem is that red dwarfs are restless. Especially when they are young, they unleash intense stellar flares and floods of high-energy radiation. A planet sitting very close in can have its atmosphere blasted, its upper layers stripped away over billions of years. And because these orbits are so tight, tidal forces usually lock one hemisphere permanently toward the star. One side an endless day, the other an endless night. Can a stable surface ocean really survive under those conditions? Or would it boil, freeze, or simply evaporate into space? So, let's begin to separate what may be doomed from what might endure. Surface oceans, wrapped in thin atmospheres, are vulnerable, but deep water layers and subsurface oceans tell a different story. Bury the ocean under tens or hundreds of kilometers of ice or high-pressure water, and the star's radiation becomes almost irrelevant. The atmosphere can erode, the surface can be scorched, and yet the interior sea remains, insulated and dark, powered by internal heat and tidal flexing rather than sunlight. TRAPPIST-1 is our best real-world test case. 7 tightly packed, rocky planets orbit a single small star only 40 light-years away. Some of them, like TRAPPIST-1F and 1G, appear low-density and potentially water-rich. Optimistically speaking, they could host vast global oceans or deep interior seas. But, while one planet might hold a steam-shrouded surface ocean, another could hide a buried one beneath ice, and a third may have lost its water entirely. So it's time to find out the truth. If most of the galaxy's ocean worlds lurk around red dwarfs, often hidden beneath ice or high-pressure mantles, where should we point our next telescopes and missions? And how do we even recognize an ocean we can never see directly? Future missions, from Europa clippers to life-finding telescopes, to answer that, we have to look ahead. If the galaxy is filled with hidden oceans, our next step is clear. We need machines that can peel back ice, read invisible magnetic ripples, and taste alien water from millions of kilometers away. So, let's begin with the worlds we can actually visit. Around Jupiter, 2 flagships are on the way. NASA's Europa Clipper and ESA's JUICE mission will fly repeated close passes by Europa, Ganymede, and Callisto. They will map the thickness and structure of the ice shells, measure how the moons flex in Jupiter's gravity, and track subtle changes in their magnetic fields. This means we can infer how deep the oceans are, how salty they might be, and even whether liquid water is in contact with rocky seafloors where chemistry for life could thrive. It should be noted that these are not just pretty picture missions. Radar sounders will probe kilometers down into the ice, magnetometers will read the electric currents induced in salty oceans, thermal cameras will search for warm cracks or plumes that could connect the surface to the deep interior. If Europa's ocean is vigorously circulating, or if Ganymede's layered seas are stacked like an underwater lasagna, we will see the fingerprints in the data. But while Jupiter's moons are the first targets, they are not the last. Dragonfly will actually land on Titan, hopping across dunes and frozen riverbeds under its thick atmosphere. It will sample organic rich sands that may have been processed by an interior water ocean over billions of years. In the hunt for alien life, Titan is a strange test case, a world where liquid methane flows on the surface while a buried ocean may host more familiar water chemistry below. And then there is Enceladus. Future mission concepts aim to fly straight through its icy plumes, collecting fresh spray from a global ocean that we already know contains salts, organics, and molecular hydrogen. A carefully designed sampler could search directly for complex organics, unusual isotopes, or even cell-sized particles. So it's time to find out the truth. If any place in the solar system is ready for a direct biosignature test, it is that tiny moon. Now, quick shift. Imagine we shrink ourselves down into a single drop of water, drifting in a young, protoplanetary disk. We freeze beyond the ice line, fall into a growing planet, are buried under high-pressure ice, and finally melt again in a dark, alien ocean. That journey is happening in countless systems right now. To study those distant oceans, we need new eyes. Next-generation space telescopes like the Habitable Worlds Observatory and giant ground-based mirrors, such as the Extremely Large Telescope, will target smaller, cooler exoplanets, including possible hycean worlds, planets with deep global oceans wrapped in hydrogen-rich atmospheres. With sharper spectra, they can pick out water vapor, methane, carbon dioxide, and maybe even oxygen in the atmospheres of ocean-bearing planets. Optimistically speaking, improved statistics from thousands of such worlds, combined with time domain monitoring that tracks seasonal changes and cloud patterns, will let us estimate how common ocean planets really are, and which ones sit in true Goldilocks zones. By comparing many systems, we can sort mere water-rich planets from those that are genuinely habitable, and then from the tiny subset that might actually host life. And as those maps of our own ocean moons fill in, and spectra of distant hycean candidates sharpen, a final question emerges: what would count as proof that something is actually swimming in those alien seas? So, what does the galaxy's ocean census really tell us? So if we really are surrounded by alien seas, what does that actually say about our place in the universe? So, let's begin by stepping back from the details. We started this journey close to home, with worlds that, for a long time, did not look promising at all. Europa, Enceladus, Titan, even distant Pluto and Ceres seemed like frozen leftovers at the edge of the solar system. But while they looked dead and airless on the surface, the data forced us to change our minds. Gravity measurements, magnetic fields, and even geysers showed us hidden global oceans, some with more water than Earth. From there, we pushed outward to planets we cannot see directly. We looked at sub-Neptunes and super-Earths whose densities are too low to be purely rock. We examined hycean candidates where a deep global ocean may sit under a thick hydrogen atmosphere, and we watched just peel back those atmospheres one spectrum at a time. This means we went from a handful of icy moons to the realization that entire classes of exoplanets could be dominated by water, and somewhere along the way, a quiet but profound idea emerged. Maybe Earth is not the archetypal water world at all. It should be noted that our oceans are a thin film on a mostly rocky planet, exposed directly to sunlight and space. In contrast, many ocean worlds seem to lock their seas under ice crusts, or bury them beneath crushing high-pressure ice, or wrap them in dense, steamy atmospheres. Optimistically speaking, Earth might actually be a relatively shallow, exposed ocean world in a galaxy ruled by deeper, darker seas. The numbers back up that shift in perspective. We see multiple ocean worlds in just one planetary system, our own. Models of planet formation suggest that a large fraction of exoplanets between Earth and Neptune size are water-rich. When you scale that up to the hundreds of billions of planets likely orbiting stars in the Milky Way, you arrive at an astonishing census, tens to perhaps hundreds of billions of ocean worlds, each with its own chemistry, its own tides, its own story. In the hunt for alien life, that changes the odds dramatically. Not every ocean is friendly. Some may be choked with antifreeze chemicals, others sealed off from starlight, others scoured by intense radiation. But with so many liquid water environments, it becomes harder to argue that all of them are sterile. Somewhere, hydrothermal vents may be feeding strange ecosystems. Somewhere, a calm twilight sea may have had billions of years to experiment. So it's time to find out the truth. If the galaxy is full of oceans, then maybe the true cosmic rarity is not life itself, but intelligence. Or perhaps, even more narrowly, it is our particular way of living on a bright, sunlit shore of a very thin, very fragile sea. And if that is the case, what does it say about the kinds of minds that might evolve in the abyss? Your turn. Choosing the most likely alien sea. So, if the galaxy is full of oceans and strange minds in the dark, which sea would you bet on first? In the hunt for alien life, this is where we hand the question back to you. Think about everything we have just explored. Europa-style worlds, with a global ocean sealed under ice, powered from below by tides and rock. Enceladus-like vent worlds, spraying their chemistry directly into space. Titan's methane lakes under a thick orange atmosphere. Hycean planets, entire globes wrapped in deep water and steam, far beyond our own solar system. Which of these feels most likely to host life, and why? We would like you to choose a side, carefully, pick a favorite class of ocean world, and defend it in the comments. If you are drawn to Europa, explain whether it is the tidal heating, the rocky seafloor, or the sheer volume of water that convinces you. If you prefer Enceladus, use the Cassini data. Those plumes with salts, organics, and molecular hydrogen are not just pretty, they are evidence of energy and chemistry at a habitable seafloor. Or perhaps you were captivated by Titan's alien lakes. Do you think life could adapt to liquid methane instead of water, using a completely different chemistry? It should be noted that this would mean a form of biology that never needs an Earth, like Goldilocks zone, at all. And then there are hycean planets, orbiting distant stars that Jay West is only now beginning to probe. Do their thick atmospheres and deep global oceans make them the best statistical bet in the universe, even if each individual planet remains mysterious? If you want to sharpen your argument, you can always revisit parts of this journey. Go back to our tour of the solar system's ocean worlds and compare Europa, Enceladus, Titan, and Triton side by side. Rewatch the segment on hycean planets and sub-Neptunes to see how we infer oceans from faint spectra and transit data. Or return to the habitability discussion, where we weighed energy, chemistry, and time, and use that framework to build your case. Optimistically speaking, this means your comment is not just an opinion, it is a tiny hypothesis in a much larger experiment. So, let's begin a different kind of observation, right here in this community. Which ocean worlds rise to the top when thousands of curious minds compare notes? In future episodes, we will take this further. We will look at exomoons that might resemble scaled-up Europas, at ice giants like Uranus and Neptune that could hide deep internal oceans, and at specific DWES targets where we may soon see hints of clouds, hazes, or even biosignature gases above endless seas. So it's time to find out the truth. Somewhere, right now, alien oceans are rolling under dim red dwarf skies, or heaving in perfect darkness beneath kilometers of ice, while our telescopes orbit quietly, just beginning to hear the echo of their waves. Tell us which sea you would sail to first, and why, and we will meet you there in the data.